Okay, this is Project Zephyr.
Zephyr.
Oh, I've been practicing this whole semester. And it's going to be on YouTube. Okay, they have designed a portable wind turbine. And it's called Personal, but it's also portable. And I would like to hand you over.
Thank you, Dr. Okcay. So, good afternoon, everyone. We are Project Zephyr. And today we will be discussing the preliminary design solution of our 3D printed personal wind turbine. Presenting today, we have myself. I'm Reese Ticketon. I'm the design team lead and electrical design lead. Along with myself, we have Adriana Jackson, the structural design lead, Brianna Larkin, the mechanical design lead, Tia Coppola, the blade design lead, and Greer Grabowski, the data collection lead. Shown on this slide is an overview of our preliminary design solution. As you can see, there are two separate configurations to our turbine. There is a horizontal configuration and a vertical. The horizontal configuration is shown on the left side of the screen, and the vertical configuration is shown on the right. These two configurations use one interchangeable base structure and one single generator. More detail about this design will be given later in the presentation. To give an overview of what we will be discussing today, we will give a project introduction and background. This will include a need for the project, any requirements, and the deliverables we have set forth. Then we will discuss the preliminary design solution, which will include the details of each system's individual design. Then Project Zephyr will talk about the project management of this semester and include anything about user budget, project budget, and labor hours put into the project this semester. There will then be a conclusion, and the floor will be open to any questions. For the better part of a century, the world has been dependent on non-renewable energy resources, such as coal and petroleum. Slowly, there has been a shift to a more sustainable future of energy, as alternative energy sources have become more common. With this shift to alternative energy, there's been an influx of large-scale sustainable energy sources. These consist of wind farms, which harness the kinetic energy of the wind, hydroelectric plants, which harness the kinetic energy of water, and solar farms, which harness the chemical energy of the sun. There are other options, but these are a few examples. While these are viable options for large-scale energy generation, the options for small-scale personal sources of sustainable energy are limited. Project Zephyr is designing a personal energy source similar to that of personal solar panels. These solar panels can power and charge small electronic devices such as cell phones or smartphones, but are ineffective when the sun is not a viable option. On cloudy, windy days when the sun is not a viable option, Project Zephyr's turbine will be a great alternative. The personal wind turbine that Project Zephyr is designing will generate 10 watts of power and 7 to 8 meters per second wind speed, or around 17 miles per hour. And the majority of the design will be 3D printed due to its accessibility and inexpensiveness. This will provide a simple, inexpensive, small-scale source of sustainable energy. While there are options for personal wind turbines available for purchase, Project Zephyr's design is intended to be open source. This means all materials, including drawings, CAD files, and build instructions, will be posted on a public outlet such as thingiverse.com or grabcad.com. This allows anyone who is interested in creating the project to replicate themselves with minimal supervision and assistance. There are 5 vital requirements that Project Zephyr must meet to complete this project. The first is to convert wind into measurable electricity. This includes generating 10 watts of power at 7 to 8 meters per second wind speed, or around 17 miles per hour, as I said before. This 7 to 8 meters per second wind speed was the average wind speed recorded in the Pacific Southwest region of the United States from the months of April to June in 2018. 3D printing will be utilized due to its accessibility, simplicity, and inexpensiveness compared to other manufacturing techniques. All 3D printed parts will be printed within 14 by 10 by 14 inches. This is the maximum size set by the Embry-Riddle Rapid Prototyping Lab here on campus. Third, the blade pitch angle, when applicable, must be able to be manually adjusted to ensure optimal angle of attack and efficiency in varying wind speeds. Fourth, the entire system must be under 15 pounds to ensure portability. This is to allow any users to easily lift the system and transport it with ease on their own. Finally, the system must operate on 2 separate axes of rotation. This includes a horizontal axis and a vertical axis. And a few examples of vertical axis wind turbines and horizontal axis wind turbines is shown on the screen. The vertical axis wind turbines, or VOTs, are shown on the left. These turbines rotate along a vertical axis or the perpendicular axis to the surface the turbine is mounted to. Horizontal axis wind turbines are shown on the right. These are HOTs. These blades rotate around the horizontal axis of the turbine or the parallel axis to the surface the turbine is mounted to. Project Zephyr will choose one VOT design and one HOT design and integrate it into these turbine system. Once the 5 vital requirements are met for Project Zephyr, there are a few optional features that Project Zephyr would like to include. This includes a system to mechanically start and slow the turbine to ensure safe operation, producing 15 watts rather than the 10 watts specified in the same 7 to 8 meters per second wind speed, or 17 miles per hour, and perform flow visualization over both configurations. This can include wind tunnel testing or particle image velocimetry testing. The deliverables for this project were split up into two semesters that the design will be completed over. The first semester, preliminary design, Project Zephyr has completed a full CAD model of both configurations, a mechanical and aerodynamic simulation of both configurations, and a LabVIEW program to simulate the data collection plan of the coming phases of the project. In the second semester of the design project, detail design, Project Zephyr will create an operation and safety manual to ensure all potential users can operate the system safely without any supervision. Project Zephyr will also create a drawing package to assist with the assembly of the turbine and create one working prototype of the system for testing purposes. I'll now like to hand the presentation off to Adrian Jackson.
Thank you, Reese. I will now be going over the structural design of our wind turbine. To start off with, the structural design is defined as a single base that will house and support all of the components of the wind turbine. There are 2 main requirements of the structural design. The first being that it must be compatible with 2 different wind turbines. This means that it must be able to support one HOT and one VOT turbine. Second, the structural design must be able to fit all the electrical components inside. From these requirements, Project Zephyr designed a 4-piece adjustable base. The 4 pieces include a top base, the middle insert, the bottom base lid, and the bottom base. These 4 pieces can be configured in 2 different orientations. The first orientation, HOT, is shown on the screen. This orientation utilizes all 4 pieces to increase the overall height of the structure. This will allow for clearance of the HOT blades while they are in use. The second orientation is the VOT orientation. This utilizes only 3 pieces of the base. To be clear, the difference between the HOT and the VOT is that the VOT does not use the middle insert piece. This will lower the height of the overall structure, which increases the stability and lowers the center of mass to compensate for the overall height of the VOT turbine. Going into more detail, this is the top base piece of the structure. This is where the motor will be housed. The motor slot and the rod holes are used to properly integrate and support the motor into the base. The bottom of this piece is threaded using coarse threads to connect to the middle insert and the bottom base lid of the structure. Next, we have the bottom base assembly, which includes the bottom base lid and the bottom base. The bottom base is where the electrical circuit will be housed. The bottom base lid acts as an adapter to go from the large diameter of the bottom base to the small diameter of the middle insert. It was designed to be removable so that the electrical circuit could be placed inside the base after being printed. The bottom base is threaded to connect to the bottom base lid, which is threaded to connect to the middle insert and the top base piece of the structure. Finally, we have the middle insert. The purpose of this piece is to increase the overall height of the structure while the hot is in use, to again allow for clearance of the blades. This piece was designed to be a smaller diameter than the top base structure and the bottom base structure to decrease the interference of flow around the hot blades. There is a slot on the side of this piece to allow for the wires to go inside of the structure while in use. To clarify, the motor will be housed above the middle insert and the electrical components will be housed below the middle insert. This slot will allow for ease of transition going from the VOT to the hot so that no wires have to be disconnected. The top and bottom of this piece are threaded to allow for connection to the top base and the bottom base lid. All 4 of these pieces will be 3D printed in the Rapid Prototyping Lab using the F370 printer here at Embry-Riddle. They will be printed using PC ABS or polycarbonate ABS, which is a composite plastic. The bottom base will be printed using a 100% infill density because it will be the most load-bearing piece. This will also help lower the overall center of mass of our piece. All 3 other pieces will be printed using a 50% infill density to lower the overall weight of the structure. There are 4 tasks that still need to be completed regarding the structural design during next semester. First, the bottom base diameter needs to be adjusted based on the actual size of the electrical circuit once it has been built. Second, a tip-over analysis needs to be performed on the structure to ensure that the system will not tip over while using the hot or VOT configuration. Based on this analysis, the bottom base feet will be either made larger and printed separately or made smaller to fit within the printer diameters here at Embry-Riddle. Finally, all 4 pieces of the structure need to be 3D printed. At this point, I will hand the presentation off to Brianna Larkin.
Thank you, Adriana. I will now present the mechanical design portion of this project. To be clear, the mechanical design of this project is the system that will allow Project Zephyr to have one single base structure holding one motor that can operate on 2 different axes. The one requirement for the mechanical design is to have one system that can interchange between the hot design and the VOT design. This means that the user will have one single turbine and can connect the hot blades to the design and run it to generate power, and then remove those to connect the VOT blades to the turbine to generate power. Project Zephyr decided that connecting the turbine shaft straight to the shaft of the motor would be the best and most simple solution. As shown behind me, is the hot orientation. The motor will be turned to face the side of the base in this, so that the shaft of the motor is along the horizontal axis for when the hot design is connected to the motor. Similarly, in the VOT orientation, the motor will be turned to face upwards so that the shaft of the motor will be along the vertical axis to connect the VOT to the turbine. For the mechanical solution of connecting the turbine shaft straight to the shaft of the motor, Project Zephyr designed a motor assembly. This motor assembly will be placed in the top base, as seen on the right, and will allow the user to rotate the motor about one axis around its center of mass. Rotating the motor about its center of mass is important to keep the system stabilized and balanced when changing from the hot and VOT orientations. The motor assembly consists of a motor housing and the motor itself. The motor housing attaches to the motor using 4 different screws at each corner of the motor. These screws will screw all the way through the motor and through the housing. Then on the sides of the housing, there are 2 holes for rods to be attached. These rods will then go through the outside of the top base, where the user will be able to turn these rods to rotate the motor. To keep the motor assembly facing either the VOT or the hot orientations, the user will screw on nuts to either end of the rod on the outside of the base to tighten it in place. Then by loosening these nuts, the motor assembly will be allowed to rotate again. The motor housing consists of 2 pieces, the top piece and the bottom piece. The top piece has a hole in the middle of it to fit nicely on top of the motor. The bottom piece has two side walls with two holes in it where the rods will be attached to rotate the motor. This picture is of a hot design that Project Zephyr got 3D printed. This was a test print so that Project Zephyr could attach it to the motor itself and test it in real wind. Doing this test was important to see if the hot design creates a large enough torque to rotate the motor, since the motor has a holding torque of 0.59 Newton meters. This means that this design will need to create a torque on its own greater than that to be able to rotate the shaft of the motor on its own in the wind and generate power. From these tests, Project Zephyr ensured that it does create enough torque in 17-mile-per-hour winds to rotate the shaft of the motor on its own. Project Zephyr will be 3D printing both pieces of the motor housing. Both pieces will be printed using a polycarbonate ABS plastic and will be printed using a solid 100% infill density. Printing both of these pieces solid will ensure the strength and stability of the motor housing. Since it is housing the motor, it needs to keep it stabilized in the system while the system is running. The next steps for Project Zephyr to complete next semester regarding the mechanical design is to test the VOT blades that will be test printed, or that have been test printed already, connected straight to the motor in 17-mile-per-hour wind speeds. These tests will determine if the VOT design is creating a large enough torque to rotate the motor on its own, or if Project Zephyr will need to incorporate a gear design for the VOT blades. After determining if the mechanical solution is successful in making any necessary adjustments, Project Zephyr will send the CAD models of the motor housing to be 3D printed in the Rapid Prototyping Lab here at Embry-Riddle, and then purchase any outside necessary hardware for the motor assembly, such as the rods, the screws, the washers, and the nuts. I will now like to pass this off to Tia Coppola.
Thank you, Brianna. I'll be discussing Project Zephyr's blade design. There are three major requirements that the blade design must meet. First, the blades must generate 10 watts of power in approximately 17-mile-per-hour wind. Second, as mentioned before, there must be a vertical axis design and a horizontal axis design. Lastly, the pitch of the blades must be manually adjusted by the user. To determine our blades, we started out first with the fundamental wind turbine equation. This equation was used to determine if the scale of our turbine was capable of producing 10 watts. This equation is based on the kinetic energy of the wind and does not account for mechanical or electrical losses, and is not the actual power output of the wind turbine. Tip speed ratio was also used to determine if we were getting adequate rotational speed. On the left of the screen is published data. It correlates the coefficient of performance with tip speed ratio for different blade types. Estimating our coefficient of performance, we can use this published data to determine our tip speed ratio and therefore determine an estimate of our rotational speed. For the horizontal axis design, a traditional 3-bladed wind turbine was chosen. The 3 blades were chosen based on a slightly higher efficiency compared to other number of blades. Based on the method I just described, there is a 1,100 rotations per minute estimated rotational speed. Each blade was designed using a NACA 63-215 airfoil. The profile of the airfoil is shown on the bottom of the screen. This airfoil was chosen to produce lift at low wind speeds. And the maximum lift drag ratio is approximately 29 at an angle of attack of 8.25. This is at a Reynolds number of around 20,000. The hot design consists of 4 parts, the 3 blades and the inner nacelle. The nacelle is shown on the top left of the screen and contains 3 holes in which the blades will be inserted. The blades are secured from the back using threaded holes and set screws. These set screws allow for the user to manually adjust the pitch of the blade if they choose to do so. For the vertical axis design, a hybrid design was chosen. The Savonius blades in the center operate on drag forces. They operate at lower wind speeds, however, they have a very poor efficiency due to operating with drag forces. The Darius blades were added to increase efficiency. The Darius blades were not the sole blades chosen because they do not operate at the wind speeds we will be operating in. The Savonius blades consist of 2 tiers. Each tier has a 90-degree offset from the bottom tier. Each tier contains 2 cylindrical cups facing in opposite directions. Due to the large scale of the part, it will have to be printed separately, as shown in the middle slide. There are slots on the bottom 2 plates for the top to be inserted to prevent it from falling apart. The top of the Savonius has a notch for the Darius mount to be connected to. Additionally, there's a slot on the very bottom for the motor to be directly connected. The Darius blades will be connected using the mount. The mount consists of 3 arms with rods sticking out of each arm. The rods are then connected through holes in the blades and then again are connected through set screws. This again allows the pitch of the blades to be adjusted by the user. Due to the large scale of the blades, it will have to be printed in 2 parts, as shown on the photo on the left. It will be connected using rectangular notches and rods and will likely just be glued together. An ANSYS simulation was performed on the blades. The photos above show the pressure contours of applied wind speed of approximately 17 miles per hour. The orange areas are high pressures, and the blue are lower pressures. As you can see, the higher pressure is building up on the front of the blades, and then in the Savonius, it's building up in the cups, which is what we want. All the parts will be printed using the same PB ABS plastic at approximately infill of 50%. This is mostly chosen to reduce the weight. Future work to be completed for the blade design. All parts must be finished printing and then tested to ensure we're getting the proper rotational and torque. Hardware must be purchased and also assembled, and then also the torque of the set screws will have to be determined to ensure that the user will not crack the plastic. I'll now discuss Project Zephyr's electrical design. The electrical design is what converts the kinetic energy into actual usable electricity. There are 2 major requirements. First, it must generate the 10 watts of desired output based on the rotational speed and torque from the blades. Second, Project Zephyr is assuming that the user will have limited electrical knowledge, so the circuit must be as simple as possible while still meeting the 10-watt power requirement. The selected generator shown above, a 2-phase stepper motor, was chosen based on its higher efficiency at low speeds, compared to DC motors that have mechanical losses due to brushes. It's a NEMA 17HS class motor. These are generally lower in cost and also smaller in weight. As Brianna mentioned, there's a 0.59 Newton meter holding torque, meaning that we'll have to exceed that torque in order for the motor to shift steps. It's 2 amp input rated and output rated. To ensure accessibility of the circuit, Project Zephyr will provide 2 options. First, the user may manually build the circuit if they wish. We'll have the design for them to go off of. Additionally, we will design a printed circuit board, or PCB. If they do not wish to print the board or build the board themselves, they have the option to buy it. This is the circuit layout. From the mechanical load, the motor will start turning, producing 2 AC currents. The The AC currents are ran through 2 full-bridge rectifiers. These rectifiers convert the AC current into DC current. The 2 signals are ran through a series of capacitors. These capacitors further smooth out noise and fully ensure a DC signal, and additionally the signals are combined at that point. The signal is run through a 5-volt buck converter. This is a voltage rectifier, meaning that there'll always be a 5-volt output from that point. As long as there's a 6 to 30 volt input, which Project Zephyr believes will be sufficient. This circuit was tested using 2 2200 microfarad capacitors. Additionally, the circuit tested did not use a voltage regulator. It was tested by putting an electric gel onto the motor and then turning it. The rotational speed was measured using a stroboscope used on a smartphone app. The results on here are perhaps not the most accurate due to inconsistent torque on the motor from the electric drill. These are the results from the test. At around 265 rotations per minute, the power output was approximately 1.45 watts. And going up to 1400 rotations per minute, the power output was approximately 12 watts. As I mentioned previously, the estimated rotational speed of our blades is around 1,000 rotations per minute. Future work to be completed, the circuit must be built and fully tested, along with the design for the printable circuit board to be manufactured, and then integrating the circuit into the bottom base and the rest of the turbine structure. I'll now pass it off to your class.
Thank you, Tia. I will be talking about the data collection program for Project Zephyr. Based on the request for proposal, or RFP, Project Zephyr is required to measure the torque of the motor and the input wind speed. However, to properly and appropriately simulate and model our wind turbine, Project Zephyr has concluded that there are 7 necessary measurements: the rotational speed on the motor, the torque of the motor, the tip speed ratio, input wind speed, power input, and power output. From these 7 data sets, Project Zephyr has concluded that there is 4 necessary instrumentation devices. For the rotational speed, a stroboscope will be used. From that, the torque on the motor, the tip speed and tip speed ratio will be calculated. For the wind input speed, Project Zephyr will be using an analog cup anemometer. For the power input, an outlet power meter. And for the power output, a USB power meter. In addition to instrumentation devices, Project Zephyr will need a data acquisition device, or a DAC. A data acquisition device is simply a device that connects instrumentation devices to the program on the computer. Project Zephyr will be using a National Instruments CDAC NI 9219. This was chosen based on its ability to acquire multiple signals at a single time. This will be used with the cup anemometer for wind input speed. The analog cup anemometer outputs a voltage, so the DAC will collect the output voltage and transfer that information to the computer. Project Zephyr has chosen to use LabVIEW for our data acquisition program. LabVIEW is a program that takes collection of data, converts the data into useful information, makes any necessary calculations, and displays the data as needed on a screen in real-life accurate time. On the screen is the current block diagram for Project Zephyr. There are 2 subprograms, subprogram A and subprogram B. These will be covered shortly. The most important block on this slide is this block right here. This block allows for Project Zephyr to write all of our data sets into a single Excel file for further analysis. This is the LabVIEW interface that Project Zephyr will see during testing. In the top left is a speedometer, where we will see the input speed from the anemometer in meters per second. As previously said, we're looking for 7 to 8 meters per second. On the right side of the screen are 4 places to input data. This is for the input power, the output power, the stroboscope in revolutions per minute, and the radius of the blades in meters. These are necessary because these are not devices that are able to connect to the DAC device, so we must input them ourselves. On the bottom of the figure are 5 information blocks that we will be seeing: the wind input speed in meters per second, the torque in Newton meters, the tip speed in meters per second, the rotational speed in radians per second, and the tip speed ratio. Additionally, there are 2 buttons that Project Zephyr will be using. The Save Data button allows for the data to be written at that instant onto the Excel file, and the Stop button allows Project Zephyr to stop collecting data from the anemometer at any moment. These are the 2 subprograms. On the left is subprogram A for the anemometer. As the anemometer has a voltage output, this program converts the voltage output into a wind speed in meters per second. This is based on the published data correlation from manufacturer's data sheet. On the right side of the screen is subprogram B. This simply converts the revolutions per minute into radians per second. On the screen is the testing method for Project Zephyr. We have the opportunity to use 3 different wind inputs: a centrifugal blower, a standing box fan, and natural winds. At location 1 is the outlet power meter. When using the centrifugal blower or standing box fan, this will be plugged into the wall outlet and the wind device will be plugged into that. Then we have our wind source and our wind moving towards the cup anemometer at location 2. This is placed between the wind source and the wind turbine so that we can gauge an accurate wind speed going into the wind turbine. At location 3 is the USB power meter. This is connected between the output of the wind turbine to a device that is being charged during testing. Location 4 is the stroboscope. The stroboscope will be handheld off to the side as to not impede the wind flow during testing. There are 4 future tasks for Project Zephyr to complete during testing for Project Zephyr. First is to confirm the accuracy of the LabVIEW program. Having an accurate simulation and model of the wind turbine will ensure that we are properly gauging how our turbine is working. Second, Project Zephyr needs to calibrate the instrumentation devices. Having our devices calibrated and working properly will ensure minimal error during testing and minimize any possible uncertainties. Third, we will test the hot and bot designs at varying blade angles. This will allow correlation to be determined and determine the best blade efficiency and best angle for that angle of attack, as Tia previously mentioned. Finally, we will analyze our data to confirm that our theoretical values calculated are comparable to our actual values being collected. I will hand the presentation off to Reese Tipton.
Thank you, Greer. I will now be talking about the project management of the project so far this semester. Project Zephyr was assigned a budget of $875. This budget encompasses all purchases from preliminary design to detailed design. Anything that is purchased must fall under this budget for both semesters. The items that will be purchased or have been purchased for Project Zephyr so far are listed in the table on the screen. So far, Project Zephyr has purchased the buck converter for the electrical circuit, the cup anemometer for the testing setup, and the USB power meter for the testing setup. All 3 of these items add up to $65.54. All other equipment needed so far has been provided by outside sources. This includes from lab. These outside sources include from labs on the Amarillo campus, donations from professors, and donations from team members. 3D printing would also take up a large majority of this budget, but the rapid prototyping lab on campus has stated that as long as the prints are approved by a supervising faculty of the rapid prototyping lab, they will not fall under the Project Zephyr budget. While Project Zephyr has $875 to complete this project, the goal of the project is to keep the price down as low as possible to ensure as many users can afford it. With that being said, Project Zephyr has created a user cost for each configuration of the turbine. The expected cost of the hot design is around $87.82, and the expected cost of the VOT design is around $134.38. While Project Zephyr has chosen to use PC ABS for testing purposes, this calculation was done with regular ABS plastic for its lower price point. 3D printing materials still takes up most of the cost of the project cost, so Project Zephyr will have to look into reducing infills or reducing sizing of the turbine designs to ensure as low cost as possible. Project Zephyr has currently worked, as of December 3rd, 2018, Project Zephyr has worked 883 1/4 hours. This plot on this slide shows the actual hours Project Zephyr has worked compared to the projected hours Project Zephyr was expected to work. The actual hours Project Zephyr has worked is shown in green, and the projected hours is shown in blue. Project Zephyr has worked 113 1/4 hours over the 700 hours expected of us so far, and hopes to continue this trend of hard work into the next semester. To conclude our presentation, Project Zephyr is designing a 3D printed personal wind turbine. This wind turbine will generate 10 watts of power and 7 to 8 meters per second wind speed, or around 17 miles per hour. The design is intended to be open source, so therefore this will be a solution for a simple, inexpensive, small-scale, sustainable energy source for anyone who is interested. For future work to be completed, Project Zephyr must experiment with infill densities to ensure the strength and weight and cost of the turbine is optimized. Project Zephyr must also perform a tip-over analysis to ensure the turbine does not fall over during operation, develop a prototype and test this prototype to ensure all requirements are met, further test blade designs to ensure optimal conversion of wind energy into electrical energy, write an operation and safety manual to ensure safe operation of the users with minimal instruction and supervision, and create a full drawing package of the project to assist with the project assembly. At this point, I'd like to thank everyone for coming and invite my colleagues up to the floor to open for any questions.
Nice job, guys. Thank you. Couple questions. My first one is related to how are, in both setups, the hot and the VOT, the blade portions mounted to the motor. So the motor has a shaft, it's got a very small flat portion, it's usually designed to have like a bolted system or something on it. How is the plastic kind of interfacing with that, and have you had any issues with tolerances or slip or something like that?
So we are planning on using a set screw for that as well. And we've mentioned that for attaching the blades to actually the cell, but we were planning on using a set screw to attach it to the shaft, to the flat shaft as well.
Okay.
And for tolerance issues, we actually, for printing our prototype on this, we did experience those. Because 3D printing has clearances, we did this as an experiment to see if just printing it as is would help, but we do have to alter the design a little bit, as we tested the hot design, the one on the table over here, with a clearance of 0.05 millimeters, and it has a perfect press fit into the system. So with the set screw, it should hold it in place. So that's what we're going to do for next semester.
Okay, cool. In the VOT configuration, maybe I'm not totally understanding this, but the way the blades are mounted on the base with the motor, what is preventing the torque from damaging the motor, or I'm not even talking about tip over, I'm just talking about the forces on the blade shaft, on the motor shaft itself. Have you done any analysis or?
So we haven't done any analysis, but we were going to look into creating a support structure for the shaft of the VOT. So as the motor is pointing up, there will be a support structure going to the actual shaft of the VOT itself, excuse me. And
is the idea to have that really close to the motor, or have something that goes all the way up and around to the top end, supporting it on both sides,
to reduce cost of 3D printing material, probably closer.
Okay. Yeah, that would be one practical, I think, consideration or problem I see coming up with it. What testing have you done with the hot design? You've done some spin tests, I see some pieces here. Can you talk a little bit about the actual testing that's taking place?
Yes. So we initially did very basic tests of the hot design with a previous design. This is a newer design with a thicker blade for more surface area to create more torque. But we initially attached the previous design to the motor and held it out of a car window at 17 miles per hour. And it did indeed spin, so that does prove that we have enough torque to spin the motor at the specified velocity. So we do not have an exact number of torque, but we do have evidence that it does in fact work. That's to be determined.
Okay, interesting. And then slide 50, can you look at that? Sweet. Are we going to produce 10 watts of power?
Yeah, so this table does kind of make it confusing. I can see how that is, because it does say at the estimated wind speed of around 1,000 RPM, we do have a power output of 5 watts. But with the buck converter in our circuit, that actually will change any voltage output from 6 volts to 30 volts to a 5 volt 2 amp output, which is 10 watts. So it's a voltage regulator and a regulator essentially.
Is that how that works?
As far as I understand from the research that I've done, if I'm incorrect.
So if I just change the voltage, I can have as many watts as I want? Is that kind of my understanding?
So it's
maybe I'm not understanding you, but what I'm looking at in this chart, it says, I'm looking at the third line there, which is 1,050
yes.
RPM line, because those are the closest to the two estimates you put for your hot and bond design. And it says 5 watts. It's about half. The 10 and the threshold 15 seems far away. You're confident though that in the end you'll get to the 10 watt number as far as your output on the
Yeah,
USB.
keep in mind this was using an electric drill, which has a much lower torque. So we can increase torque will like hook it up to the
Ooh, but when you're actually converting it, all you're worried about is your RPM into that Zephyr motor, right?
The buck converter, the way it works is that if you have any voltage input between 6 volts and 30 volts, it will automatically output 5 volts and 2 amps. So really the most important column on this is the right column, or the left column for voltages, which is at about 1,000 RPMs, we have a voltage of 9.8, which is in that range. Therefore it will be outputting 10 watts.
Okay, I really think
I feel like there's some confusion.
Yeah.
Equal IDs.
Okay. Yeah, so those are some of my base questions. So
We can talk about it further after the presentation if you'd like. We can go a little bit more in depth and possibly correct our math.
thank you.
Thank you.
Nice job, guys. So a couple basic questions about the structural design. So we can go to 15 and just talk through. So just kind of a general blanket question for this. How are all your parts sized? Do you do some kind of structural analysis, hand calcs? How did you get these dimensions from the requirements you were given for the individual parts?
These dimensions were more based off of the clearance of the blades. So for our hot design, we did actually do calculations to find the minimum blade length we need to get the blade sweep area for our potential power output, as Tia was talking about with the potential wind energy. So therefore, the height of 365 millimeters is to allow clearance of the blade length from the bottom of the base.
Okay. Well, so going to, let's get a good picture of the lot. Let's go to 25. So how much does the lot itself weigh about?
That we did not do. Actually, in CATIA, I did find, by changing the density of the ABS in CATIA to around 75% of the density that's programmed into CATIA to simulate the infill density of 3D printing with a rough estimate of varying between 50 and 100% for our infills. The entire assembly was 15.15 pounds. So our requirement is 15 pounds for the entire thing. So therefore, as we were stating, we were going to change the infill densities and possibly sizing to meet that 15-pound
Okay,
requirement.
so correct me if I'm wrong, but then you said that you're planning this thing can spin up to 955 RPM. So you said that, right?
Yeah.
Okay, so you mentioned something about the fan at the bottom, but I kind of want to bring up another consideration. So that's a lot of mass spinning really fast, and I wanted to know if you guys thought, is there a possibility to run into some vibration or structural instability issues, and like this thing just starts going like crazy, need some sort of vibration?
We were going to do a vibration analysis on the blades to ensure that they don't break themselves.
Yeah, you might want to look at that and then do like I know you can do, you're limited in the types of modal analysis you can do, like you're not going to do like a ground vibration test on it probably. But you could do that in ANSYS at least or something like that. Those are the natural frequencies to make sure you're not stepping in any of those in your range of operating conditions, maybe figure out how fast this thing should actually spin, make a recommendation. But just so you know, you're definitely going to want to look at that.
Thank you.
And then I had a couple others. So when you said you're going to test the whole thing 17-mile-an-hour winds, you said you put out the car window earlier, so were you just going to do that again, or were you going to wait for a day?
So as Greer was talking about, we were going to have either the centrifugal blower that's located in the top black, or a box fan that we could measure the wind speed out of to find the problem.
I just want to make sure you weren't waiting for a 17-mile-an-hour. Okay, so is that it, I think? Oh, and then you had something in your cost analysis. And it was just kind of a consideration. So you said you're basically planning on doing a one-to-one for your cost estimate, right? So like if it costs us this much, we're going to sell it for exactly this much. Is that kind of what you're thinking?
Yeah, so it's not, we don't plan on selling it as a product. It's something that will be published online, and we'll give exact values for the pricing of each component. So this is how much it'll cost to print it by yourself.
Oh, okay. I see.
Yeah, we won't be selling it ourselves. It's something that people can go out and make themselves.
Okay, gotcha. Okay, well, I think that was all I had, so thank you guys.
Thank you.
Good on that, very nice job. I was, especially like the open source idea, I mean, that's really clever. And being the energy track, it's like how to come up with a capstone project. They did a really good job with the concept of the project. A little unclear on the source of some of the requirements, so like the 10 watts, where did that come from? Does the solar thing that I have in my backpack, is it 15 watts?
This was based off of just power output to charge or power a small electronic device. So a 5-volt 2-amp output to charge a cell phone or small electronics and stuff like that. So I'd be 10
I
watts.
just didn't think my thing did 10 watts, I didn't understand why you used that thing. And then, the weight requirement of 15 pounds, that's probably pretty arbitrary also. The solar thing's a lot lighter than that. So 15 pounds in the backpack. The real key though, you talk about, I forget the number of the machine that you're printing on, but it's a very expensive machine. And so if you're trying to make this open source for anybody can go do it, lots of people have MakerBots. Did you look at trying to build it within the space of a MakerBot?
Yes, so the maximum specifications are actually set for the Type A printers in the rapid prototyping lab. So the F370 is the very expensive printer that prints in the PC ABS, and the Type A actually prints in ABS and PLA. So it's actually a less expensive printer to run. So that's what we were basing off of. The
Type A is out of business, it's really the MakerBot that you need to look at.
I don't know the company of the Type A, but it is just a general 3D printer that people
They
can.
went out of business last year.
Did they?
Went through a whole mess trying to get those machines maintained. Everybody's got MakerBots.
So the design that we currently came up with is actually because the motor already has holes going through it with screws in it, so it's just a simple solution. Get a longer screw of the same thread and just make it go through the plastic itself and just put a nut on the other side. So it's using the already available space inside the motor.
Well, I have nice job.
Thank you.
John, I have a question for you. Far more educated in power than I am, so I just felt like it was never answered adequately at the start. Why do you consider it a requirement to have a vertical and a horizontal orientation? Why wouldn't you just offer one or the other?
That was actually included in the project as an educational benefit for us. So for educational purposes, for us to actually get more experience with mechanical design, designing a system that can rotate along one axis and change to another axis. So there was no basis for the product itself to have that, but it was more to make the project more challenging for us, essentially.
They consider it too simple if you didn't do
So we just make a spin.
Have you attempted any kind of calculation to figure out at what point it would pay off to sit home and build one of these as opposed to just plugging in to the wall?
We have not, because this is more of, it's almost a demonstration purpose system. It's more of okay, well, we're out camping, just like with personal solar panels. We can set up the small wind turbine to power small electronics and stuff like that. It's not designed as a replacement for wall outlet power. It's more of just okay, I'm out in the open, or I want to just use it. It's more of a just interest kind of thing. Anyone who's interested in the project.
Not foreseeing a farmer needs a house, somebody can.
Not in this foreseeable future.
So are you going to set on your product, are you going to set a maximum wind speed if the forecast says 50 mile an hour gust, you can recommend people live in the wind?
That would definitely be a good thing to consider, and we will definitely do that in the future. Test it until it breaks.
The stepper motor, how do you discover that the stepper motor would work better than a DC motor or generator as a
This was based off of more research into similar projects. There are people who have made small-scale wind turbines just with a stepper motor. Most people do not use DC motors, as Tia mentioned. They have losses due to brushes, and stepper motors are more efficient at the lower speeds that we plan on spinning.
in the research, does it sharpen the light using the stepper motor backwards like that? Or?
Not from what we found. The only issue with stepper motors is at the bearings. There is a bearing in the motor that can wear out after some time if there's a load on that, compared to just turning something. It's being turned with a load, so that might affect the lifespan of the motor itself, but we have not found anything in our research for that.
I guess you're relying on your, what was it called, the unit that converts the voltage to 5 volts.
The buck converter?
Buck converter, yes. Is it, so it'll protect the user's equipment against any type of voltage?
Yes, so it has a fixed 5-volt output, and we have to go into more testing to ensure that it does give us the 10-watt output that we require.
Is there any way you'll be hitting it with more than 30 volts DC? And will it burn out there?
Based on our calculations from the motor testing results, at a rotational speed of 1400 RPM, we only got a voltage input of around 18.6 volts, I believe the number was. So we don't expect the voltage to get up to the 30 volts.
Sounds like a low number before you get going so fast.
Yeah, that might be an issue as well. That's why we're doing the tip over analysis to ensure it doesn't blow.
One suggestion, if you do a future presentation, study up a little more on voltage and current and what kind of power you can get out of it. So picture chart. Other than that, it's great. So,
Thank you.
On that chart, is the motor sitting on the bottom of that little holder, or is the weight sitting on the two pins?
The weight currently, the way it's designed, it is sitting on the 2 pins, so we will have to do some sort of stress
That's just
analysis.
one of those ones that jumped at me.
Yeah.
And otherwise, everything else was really fun.
Thank you.
Good job. It's an interesting concept. I worry about 1400 RPM. What about safety?
So that's something that we will have to include in the safety, operation and safety manual next semester when we create that. We will have to specify that it has fast spinning components and don't get your hands in there anywhere because it could hurt you. And we will also specify safety restrictions for the electrical circuit as well. The turbine will probably break if it hits anything, so
We picked that was my next question.
yeah, so I mean, if it hits any person, hopefully it does not. It will probably break before it injures someone drastically, but that is not something we want to happen. So we will specify in the operation and safety manual that you have to be cautious when working with it because it can hurt you.
So in your analysis, is there a for the hot, is there a wind speed at which it will tip over? Do you know what that is?
Not yet. That's why we are going to perform the analysis to
Because
determine.
rarely have nice steady winds. You'll have a gust or something or it'll change direction. Do you have any compensation? Do you have anything that will allow it if the wind direction changes or you just duck your head and move?
For the hot design, not yet.
Good job. Thank you very much.
Thank you. Any other questions? Rachel?
Yeah. Have you done an analysis for, say, a user has, say, a different motor that they want to be able to use in this? Have you done analysis of performance with different motors and possibly will offer alternatives to users? I know it's going to be open source, so people might want to make that change. Is there any analysis that you can provide as to what the performance might look like when they do that change?
We actually did analyze a same class motor in the NEMA 17 HS class, but a lower holding torque and lower rated amperage motor version. It did not, even at the 1,400 RPM range, as with this one, we got 12 watts out of it. That one only got around 8 watts out of it. So we haven't analyzed another motor, and that's why we went with this one, because it is a little bit more powerful. So we can specify this is the one that it is designed for, but if you choose to use another motor, you might not get the same outputs.
Okay.
Question. You talked, I think, about like a manual brake of some kind to be included in the future. Is that an optional design consideration or a required design?
At the moment, it is optional, but personally, I really want to include it because it could really hurt someone if it's spinning out of control.
I'd start making that choice of requirement because you've got to figure out a way to slow this thing down when you need it to.
Safety will definitely become an issue during operations.
No, it's not going to be an issue. It's not going to be an issue.
A concern. That's a better word.
I look forward to seeing this one happen in my life.
Appreciate it. Any other questions? Thank you so much. I really appreciate it.